Hello and welcome again to the podcast. I'm very pleased to be joined again by my good friend Hugh Waters, down there in the Skype window below me this time. We've upgraded Skype versions this time. We can't get the video windows to behave themselves, but I think it's kind of good enough. We can see Hugh in all his glory, looking fine on his outboard camera. He was showing me the second camera earlier, but we're going to resist the temptation to vision mix and do all that kind of stuff, because this really is about the screen content and the websites and the pictures we're going to show you. So welcome once again. And I'm going to throw over to Hugh now, so he can remind you who he is and tell us a little bit about what we're going to be talking about today.
Okay, well, I'm Hugh Waters, and these days I'm a consultant, have been for the last decade, talking about all sorts of things to do with television and post-production facilities and stuff like that. I used to run a little post house in London. So, what we're going to talk about today is a very sexy subject. It's one of those things that I think is going to hold television together for the foreseeable future. Yes, it's mains. Okay, it's not that sexy, but Phil, I know that you are a bit of a champion for taking safety seriously, and particularly for taking main safety seriously. I was just looking at it, at the notes that I've got here that you scribbled down, and I see that these things are something of a throwback to the 60s, isn't that right? Sort of the left-wing nanny state. Well, suddenly bringing in regulations.
You say the 60s. It's actually the 1860s. It goes back that far. So I've just popped up on screen. I'm just going to zoom into it. The first edition of the IE wiring regulations for electrical safety, and they were in fact 4 sheets of A4 back in those days. And we see here the rules and regulations for the prevention of fire risk arising from electric lighting. And this is what was the very first edition of the IE regulations, which is with us all the way till now, and now we find ourselves with the 17th edition, which has been around since the summer of 2008. I went and did my refresher training back, what was that, nearly 4 years ago, 3.5 years ago, for electrical installations, for both domestic and professional premises. And in fact, I've just popped up the IET's page on the 17th edition wiring regulations, otherwise known as BS 7671. And although they're not a legal requirement for anybody really, you would have a jolly hard time in court if somebody had died on your watch from an electrical fault or an accident of that kind. And as broadcast engineers, as media technicians, we have a moral obligation to make sure that this regulation in particular is being complied with. If you're a chief engineer, even doubly so. You should know. You should have a copy.
But even as a board director. Yeah, I mean, even as a board director or as the MD, I would think that you would need to look to see who's carrying the can there.
Absolutely. Did somebody say corporate manslaughter? That's something that happens. People get dragged in front of courts, and even though they had no part in what might have gone on to cause an unfortunate accident, there is this thing called corporate manslaughter, and if you're a board level, technical director or even a non-technical director, you have an obligation to make sure that your people are providing a safe environment, not only in electrical safety, but in control of substances hazardous to health, the COSH regulations, as well as other things. But obviously, we're talking about electrical safety today.
Okay, yeah, absolutely. And I think probably at this point it's a good idea just to have a quick backtrack and talk about electricity itself. How are we generating and why is it dangerous? Is it dangerous? I thought the whole idea of the change from DC to AC made it less dangerous. So what are we fussed about?
Well, there are some fantastic stories about Edison so who's the other chap? Was it Marconi and Edison? I'm not sure, but two of those early Victorian engineers who sort of battled each other
as well. Yes.
Well, and there was a lot of contention as to whether DC or AC was the best kind of electricity for safety purposes, for distributing to the household. But I mean, we find ourselves with 240 volts AC in Europe. Obviously our American cousins operate at 110 volts, and in fact, if you've ever been on a building site, you quite often see 110 volt step down transformers for powered hand tools and other things used on building sites. But Electricity is deadly. 50 volts is enough to stop the human heart. If you're unfortunate enough to get a shock in just the right place across your chest cavity, 50 volts can disrupt the operation of the human heart, because that's exactly how the heart works. It works by electrical impulse, causing the muscles to contract and make you work. And of course, the other thing that is a safety risk from electrical shock is burning. So principally disruption of the heart and burning. And I don't know if you've ever noticed an electrician, when they're working, if they're having to work on a live distribution board, you see them lift the foot opposite the hand that may come into contact with a live conductor. And that's because they know that should they get a shock down that arm, the path to earth, they would really rather it was down one side of their body and not across their chest cavity to the other side of their body, and thus they improve their chances of not dying should they get an unexpected electrical shock. So
I remember being taught something similar when we were working on old 1500 chassis, which you won't remember because they're black and white sets, at college. And yes, keeping one hand in your pocket so you couldn't bridge yourself across two nasty bits of live chassis.
Well, of course, CRT monitors, huge voltages in the back of them. A black and white monitor. What's it, 18 kV to accelerate the electrons down the tube, and about 27 kV for a colour monitor. Thankfully, CRT monitors are almost gone, and so the chance to be killed by those huge voltages is disappearing. I think the other thing because my kids are all teenagers, and so we're sort of often talking about physics and things like that, and they want to know a good analogy for electricity, because electricity isn't hugely intuitive. It's not something that particularly you have a good feeling for. And I think the analogy of a water flowing through a pipe is an excellent analogy. So the rate of flow of the water is equivalent to the actual current, and the pressure of the water, how hard that water pushes through the pipe, is the analogue of the voltage, the potential difference. And of course, no water flows if there's no pressure, in the same way that no electrical current flows if there's no voltage, if there's no potential difference between two parts of a circuit. And similarly, if you try and push too much pressure down a water pipe, if the pipe isn't a good enough conductor of the water to withstand that, it will burst, in the same way that an electrical wire, if you try and push too much current through it by virtue of putting a too large a voltage across it, will burn out. So if as you think about these things, the analogy of water flowing through a pipe is a very good one.
Yes, indeed, it works very well indeed, and yes, and you can now visualise putting in a safety device to trip the water pressure at this point instead of earlier on or later on. So yes, which takes us neatly to putting in some safety devices and having things break on purpose.
Yes. So we'll in a little while we'll talk about the different classes of electrical devices and how legally things have to be built so that they're considered safe. But the two things you commonly find, both in domestic and in professional installations, are well, of course, if you go back many years, you would have been used to seeing big fuses in the distribution board. A big Bakelite carrier with a couple of prongs on it and a piece of fuse wire screwed between those two terminals. Those have largely disappeared. You may well come across them in very old buildings, and are replaced by what I have up on screen at the moment, which is what they call an MCB, a miniature circuit breaker. And let's just zoom in on this so it's a bit clearer. You can see it's marked. This one is a C16 MCB, so that will notionally pop at 16 amps. It's very typically rated for maybe a ring main circuit in a domestic premises where you might have a few plug points off it, or that is a very, very typical breaker that you might find feeding an equipment rack or an editing desk or something in our environment. Now, of course, you still have fuses, maybe a couple of them in the path all the way to the piece of equipment. Typically, if it's powered off a 13 amp mains plug, it will have a fuse within the plug itself. But even if it isn't, so I've just popped up a 13 amp mains plug just for illustration. But even if it isn't being powered off a 13 amp mains plug, if it's being powered off what we consider to be a technical distribution, off a an IEC connector, sometimes referred to as a C13 or a C14 connector, which is a 10 amp connector, which is kind of specific to sort of broadcast and IT, that you'd expect that connector to have a fuse in the distribution board at the top of the cabinet. So there'd be a fuse in the way. And fuses are typically marked with the current that will cause that fuse to rupture. So it might be a 3 amp fuse or a 5 amp fuse or a 10 amp fuse. And in addition, the fuses also will have a qualifier. It'll either be a T 5 amp or an F 3 amp. And the T and the F signify whether it's what we call an anti-surge fuse, because a lot of equipment momentarily, when it's turned on, will drag an awful lot of current, but then settle down quite quickly as everything kind of springs into operation. And so, whereas the steady state draw of that piece of equipment might be an amp, for example, that momentary inrush of current might be 10 amps or greater. And so you want a fuse that's rated as an anti-surge fuse, a T-rated fuse. So that's what the T on a T10 amp or a T3 amp fuse is. Conversely, there's also F-rated fuses, which are less common, but an F-rated fuse is a fast blow fuse. And that won't hang around. As soon as that fuse sees the inrush of current, it goes. And it's all mechanical design that makes a fuse a slow blow fuse, a T-rated fuse, or a fast blow fuse. And if you ever get a glass F-rated fuse, where you can see the construction inside, and you come across them occasionally, you can see there's a little spring as part of the fuse link, and that has the fuse wire under tension, and it will pull it apart very quickly when it gets hot and starts to stretch. So that's how they achieve that mechanically. And similarly with a T-rated fuse, the inside of the fuse is packed with sand, so that it will have a kind of a cooling effect on the
bit of a heat sink there.
on the fuse element, exactly. So that's fuses. Now, a fuse really satisfies two functions. If a piece of equipment were to develop a fault and start dragging an awful lot of current, which could cause cabling to burn out and things like that, and a fire hazard, the fuse will blow, thus rendering the equipment safe. Or, more importantly, the fuse also works in conjunction with the other great safety feature that all mains powered equipment has, and that's the earth. The earth is that connection that will essentially, if the metal box of the equipment should become live because of some internal fault, maybe the internal power supply, something has come adrift and a live connection has touched onto the metal box of the equipment. Because the metal box of the equipment is also connected to this earth connection, that will sink as much current as the main supply can give it down to earth, and of course that causes the fuse to rupture. So the equipment is rendered safe, and hopefully nobody dies by touching what's now a live piece of equipment. So
absolutely.
So fuses are they're the kind of the old school method of causing that, and you typically still find those in plugs, in the distribution strips at the top of equipment cabinets, but once you get back to the distribution board that's feeding the machine room, that's feeding your house, you won't find fuses anymore. You'll find miniature circuit breakers, because as a user serviceable part, having fuses in the main incoming fuse board was never considered a great idea, and it's much better to be able to just reach up and flip the breaker back over, and it works in exactly the same way. It's a bimetallic strip. It's a thermal device, and when too much current's pulled through it, it flips and knocks the MCB out.
Is that actually still true right at the incoming point in your facility of mains? Do they have MCBs to the bus bars, or do they still have those enormous fuses? They used to have one on each phase.
Yeah, so if you can consider a 3 200 amp phases coming into a facility, which is very typical. Of course, nowadays, where we don't tend to have big, lighting gantries anymore, for the little studio, and air conditioning requirements are a lot more modest, and all those kind of things. There's increasing number of facilities where they're only operating on a single 100 amp domestic type, main supply. A lot of facilities that we work with will be that way, particularly if there are only half a dozen Avid suites or whatever, and they don't have a great requirement for 3-phase air conditioning, for example. They'll be operating on that sort of small office stroke domestic type 100 amp supply, and but even then they still have a dirty big isolating fuse on the input feed, and that's the responsibility. That is normally the demarcation of responsibility between your in-house electrician, if you have one, or the contracting company that looks after your premises, and the electricity company, EDF or whoever.
Actually, that's probably quite a good point to bring in this talk a little bit about three-phase versus single-phase. I was just thinking about some horror stories from the past where one of the three phases has blown and it's caused all sorts of things. I remember working years and years and years ago in a factory, and the lathes all started going backwards rather jerkily because one of the phases had gone. Yes, it's very peculiar.
It's true, isn't it? Well, so again, three-phase power. It seems very counterintuitive. If you were starting again from scratch, who on earth would say that's a good idea? We'll have three versions of the live feed. They're all carrying 240 volts RMS, a sine wave, but we'll make them 120 degrees out of phase with each other. It's just why on earth would you have that?
Help?
Yeah, and it just turns out that that's the best way to generate electricity. That huge, great generating plant, at the coast in Essex or wherever it's coming from, burning lots of fossil fuel to heat water, to turn a turbine, to make electricity. It just turns out that the most efficient way of converting that motive force of the spinning generator into voltage is not to have a single coil wound around the spinning magnets, but it's to have three coils and to be picking up that induced electrical current in three phases rather than in a single phase. And so as the power leaves the power station where it's generated, it's travelling out on three live cables and a single neutral return cable. So when you see those big pylons in the countryside, they're carrying three-phase power at very high voltage, and that's because it's more efficient to distribute the power around the country at a very high voltage, because the impedance in those very, very long, admittedly very high quality copper lines, but there's still a certain number of ohms per mile of resistance to the electrical current flow. If you're going to lose a certain number of volts across that distance, we'd rather lose them at a very high voltage so that the effect on our power is minimised, because as every engineer knows, power is the product of current and voltage, and it's just a much more efficient way to distribute stuff around the world. And of course, when it gets to the end of when it gets to the substation on the outskirts of your town, and you may know where that substation is, it's then stepped down to 11 kilovolts, still a very high voltage, and but again still at three phases, and that's distributed to substations at the ends of people's streets and those kind of things, where it's stepped down to the 240 volts per phase that then gets provided domestically. And you mentioned you can lose a phase, and if during a power cut you might have walked out into your street and noticed that maybe only one house in three has its lights turned off. That's because one of the phases has gone. Maybe the red phase has been lost at the substation or further upstream, and so the effect you get there is that one house in three no longer has any power. And like you say, in a factory where you've got machines that rely on three-phase power, where there's a three-phase supply coming into the factory, and in the same way that it's very efficient to generate electricity at three phases, lots of big machines that that have big motors that turn things, they work most efficiently with three phases. So rather than having a single wound coil around the assembly of the motor, it's much more efficient, and the motor runs more smoothly if it's got three phases.
Yes, absolutely. That just reminds me, for some reason, the only piece of broadcast kit I ever found with three phases, apart from air conditioning, was a Spirit Telecine. I can't remember why it had it.
Yes, even as recently as the Spirit 4K. So this is a job that we'll both remember. Installing a Spirit 4K in a facility in Soho, and in fact, eventually, because there were fewer and fewer facilities that had proper three-phase power around the building, I think they introduced a single-phase power supply variant of that machine, which dragged three times as much current, but only on a single phase. And I think they even have an arrangement where they generate the three phases inside the big power supply unit for the machine, and so the machine's still a three-phase device, because you need that very smooth rotation of film spools and all the other rotating pieces that make a telecine work nicely.
That putting a lot onto one phase just leads me to a note that which surprised me, which I hadn't realised, which is about money. If the management doesn't want to take responsibility for safety, wave the bill under their nose.
Yes, well, I mean, you mentioned the factory that you worked in, where there was three-phase equipment, because if you think about the way that the power is distributed, they want as much balance between the phases in terms of electrical loading as possible. The electricity company doesn't work well for them if they're having to deal with, a demand where there are many more hundreds of amps going out on one phase than the other phases. So they will try their best to balance up the loads. And of course, all they can do to their customers is to financially oblige their customers to do it. So if you have a three-phase incoming feed to your building, the electricity company are not measuring the number of kilowatt hours you're using off each phase and billing you for that. They're saying, which is your most heavily used phase, and we bill you 3 times on that. So, yeah, indeed, yeah. So there was a studio I worked at in St John's Wood in the early 90s, and at one point, because the MD thought that the electricity bill was very large, I was tasked to find out why. And putting a clamp meter on the 3 incoming phases in the lines room, I discovered that we were pulling about 150 amps on the red phase, 20 amps on the blue phase, and only a few amps on the yellow phase. And of course, we were paying as if we were consuming a constant 450 amps, which was more than twice what we were really using. And it was all because we had the studio lighting grid and the main machine room on the red phase. The edit suites and the domestic mains were sitting on the blue phase, and just general lighting was on the yellow phase. So, at some point, an electrician had made that decision. Oh, that must be the best phase to put all this technical gear on. But of course,
we were scared of putting stuff, certainly that it might be reached, on more than one on a single phase. We built all our machine rooms so that everything, as far as possible, was on the same phase. We were terrified that you would have 2 phases within reaching distance. Is that not important?
No, it's absolutely true. In the 16th edition of the IAE regs, which got revised 4 times throughout the sort of the 90s and the noughties, I think the first 2 revisions of that actually forbid you having phases too close to each other. And in fact, I can remember going for a promotion interview when I worked at the BBC, and the engineer who was conducting the interview said to me, "How close are you allowed to have 2 different mains phases?" And I couldn't for the life of me remember what the spec was, but I just said, about that close, and stretched my arms out to indicate sort of a couple of metres. And he laughed and knew exactly what I was driving at, and kind of gave me the point, because he knew that I understood why.
Yes.
But it's expensive. If you're obliged to run that machine room on one phase, that may well represent 90% of the current that your facility's pulling.
Yeah.
And in fact, over the last 10, 15 years, the regulation has been relaxed to allow you to do that. And in fact, now you go in most machine rooms, you go in most comms rooms, and you see the bays run red, blue, yellow, red, blue, yellow. And in fact, they intentionally put them on different phases. Now, one of the reasons why that's now an acceptable way to carry on, and I'm just popping up a picture now of a residual current detector, an RCD, is for precisely these gadgets. They look a bit like an MCB, a miniature circuit breaker, and in fact you see them on the same bus bar board in your mains distribution cabinet as you would see MCBs, but they fulfill a fundamentally different role. An RCD, a residual current detector, sometimes they're called ELBs, earth leakage breakers, is a gadget that typically sits upstream of all the MCBs, of all the circuit breakers, and whereas the circuit breaker only has a live in and a live out, an RCD has live and neutral in and out, and it sits across the live and neutral supply, and it monitors the difference between the current going down the live supply and the current coming back up the neutral supply. And if there's more than just about, well, in the case of this one I've got up on the screen at the moment, I'll zoom in so it's even clearer. If there's more than 30 milliamps of difference between the live and the earth, you've got to say to yourself, where's that current going? We're sending a different amount of current down one leg than it's coming back up the other leg. Where's that current going? Is it travelling through some poor person's body to earth?
Yes.
And if it is, we better break this circuit. We better interrupt the flow. And so
if you had your hose analogy, you've measured the amount of water going in, you've measured the amount of water coming out. Oh, hang on, less is coming out than is going in.
Yeah,
therefore there must be a leak somewhere.
The floor's getting wet.
Got wet trousers.
Yeah. And so I'm zooming right in on this, and you'll see that the marking on this RCD is a I differential n, so a current difference of 30 milliamps, and T differential n less than 0.3 of a second, 300 milliseconds. So that's basically saying if we see more than 30 milliamps of residual current for more than 300 milliseconds, we break the supply. And it's the introduction of reliable RCDs that really allowed for things like mixed phases within machine rooms and things like that, because they essentially provide an awful lot of protection. Because think about it, I'll go back to our 3 sine waves showing what's coming out of our generator and hence what's coming into our mains intake in our facility. There are times where the difference between one phase and another phase is an awful lot more than just 240 volts. You've got more than 400 volts between that negative going dip there and that positive going spike there. And that's why 3 phases are dangerous. I mean, mains is dangerous, but 3 phases are doubly so, because you can get across huge great voltage differences, not just the difference between neutral and live, which is 240 volts. You can get very much larger shocks.
Indeed. Well, so having these trips enables us to play it a little bit closer with the 3 phases, but of course trips isn't the only way of ensuring safety, and I think that rather brings us neatly onto the difference between domestic and technical mains and earthing to go with it.
Yes, well, earthing, you've got to really talk about earthing, because something that comes up a lot with audio guys is this concept of have we got a clean earth? You often hear audio guys saying that. Is this place wired with a clean earth? That's a little bit misleading, because they assume that means the old-fashioned earthing spike that's been sunk into the ground, in the yard outside. But that was the standard for mains probably until the late 70s. But for many, many years now, the earth that arrives at your facility, that safety earth, that third connection, the third pin on any mains connector. So I'll pop up a different style of mains connector just so we can. That's a C-form connector, C16 amp, otherwise known as a commando connector. That's what electricians refer to it as. The big thick pin there, that's the earth. And in fact, all the class 1 mains that we deal with has a safety earth, which comes back to the earth bus bar, at the mains intake of your facility, and if you know where the mains intake is, you could pop down. It might be in the same room as the lines room. That's often the case, and you can see where all this is derived from. But so nowadays that earth is provided by the electricity company, and in fact it goes back to the neutral point at the step down transformer at the substation at the end of your street, or 2 or 3 streets away. And that's a good thick quality bit of copper coming all the way to your street to provide that safety earth. But in the States, having an earth that's derived from a piece of copper buried in the ground outside is still common. And in fact, in this country as well, there was also a tradition of tying earths to water pipes and things like that, because that provided a very good solid connection into the ground. And the impedance between your house and the power station via the earth is tiny. The earth is a very good conductor, and that's how earths used to be derived. Not so much anymore. They're derived from a provided earth that comes in from the neutral star point at the step-down transformer at the substation at the end of your road. As we've implied, the earth is so important because it's the way that allows the fuse to blow if you're in trouble, and many a life has been saved by having the safety earth. And in those countries where they're not kind of so hot, you see 2-pin mains connectors with an optional earth, they suffer with hundreds more people dying every year because of electrically faulty equipment than we do. So earth's very important. Now, just having mentioned earths, that brings us around to this whole idea of technical and domestic mains. In your house, you have domestic mains. That's what you have, and very fine mains it is. It powers your cooker and your little laptops, power adapter and everything else. Excellent. But in a technical facility like television or a film facility or those kind of things, radio facility, we have a slightly higher expectation because we'd like to have a very clean earth for all our production equipment. So every time you plug in a vacuum cleaner or push the toaster down, that puts dirty big splats and spikes on the mains, which if you're looking for that last percent of audio fidelity or that last ounce of reliability for the data stream, for the various digital signals that are being distributed around your facility. You want to avoid those kind of splats and stuff. So it's very typical to have split technical and domestic mains.
Yes, I mean, when we were handling a lot of analog signals, you could easily see why it was so important. You'd get these splats coming across which you couldn't get rid of, even if you're just handling baseband video. But in the digital world, it's tempting to think that it's not that important, or it's considerably less important. How true is that?
Well, of course, you don't see it quite so quickly, and that's because say imagine you've got like an encoding workstation in a room, and the operator's dutifully ingesting lots of stuff off a digital VTR that's sat in the machine room down the corridor, and you could have quite a lot of noise on that incoming video signal before the card in the computer starts getting upset and starts interpreting noise as parts of the digital data stream, and you start seeing green and pink splats on your encoded video. But to have a bit more of an appreciation of why that's the case, I'm just going to talk a little bit now about the different classes of equipment.
Yeah.
Now, this is as sort of defined by the same people who define things like the 17th edition and things like that. And principally, the two pieces of equipment we're most concerned with are Class 1 and Class 2 equipment. And the little symbols that tell you, if you look on the back of the equipment, where the little sticker is where the mains cable goes in, you'll either see the little circle with the kind of earth symbol in it, or you'll see the double square. So a Class 1 piece of equipment is one where there is an earth that is connected to the metal casing of the equipment, and any equipment that's got a metal casing or exposed metal parts is going to be a Class 1 piece of equipment, and those exposed metal parts will be connected to the safety earth that goes back to the plug point, so that you know that the equipment's earthed. Now, just consider a VTR or any other piece of professional equipment where you've got BNC connectors on the back, or XLR connectors on the back, or any other kind of pro type connector. The shell of that connector is by definition connected to the chassis of the piece of equipment. So just sort of tuck that away, bear that in mind. The other piece of equipment we see a lot is what they call Class 2 equipment, double insulated equipment, often referred to as. And the rule is that there have to be two pieces of insulation between you, the person who's using that equipment, plug in the adapter into the wall or whatever, and any current carrying, any high current carrying conductors within the equipment. Now, the rule is that one of those pieces of insulation can be an air gap. So,
all right.
So within the equipment, so long as there are two pieces of insulation, which can be the plastic box of the equipment and an air gap, so long as there's two pieces of insulation, then the requirements for certification and testing and the expense of building it are somewhat less, and you can call your piece of equipment a Class 2 piece of equipment. And it's why increasingly we're finding in broadcast. So let me just grab a piece of equipment that I've got here on my desk, waiting to go back to the repairers. So I messed the camera up there. A little fibre optic transceiver. It's a standalone unit. Might sit in the back of an edit suite desk if the edit suite was located a long way from the machine room and you needed fibre optics. And return to our previous podcast on Fibre 101 for that. But this has a little DC inlet. Doesn't have a requirement for a power supply, and even though it's in a metal box, very nicely constructed piece of gadgetry, it's a Class 2 piece of equipment because it uses a plastic plug top adapter, and it has no requirement to be an earthed device, and so it'd be a Class 2 piece of equipment. And Class 1 pieces of equipment are those things which are metal cased, high voltages inside, and then by extension they need an earth, and you can see the earth is part of the Class 1 symbol. Now there is Class 3, but that's for low voltage equipment that are used medically. So typically equipment that's used in operations and things like that, and so that doesn't really concern us.
So we're generally not going to come across that.
Yeah.
Okay, well that's all fine. So now we know a little bit about the safety, where it comes from, and the earthing, and how to break it. But now let's talk about the real world and stick it into our facilities and that interplay between ourselves and the electrician who pops in.
Well, indeed. But so, if I can just sort of close off the whole business of domestic and technical, domestic and technical and supplies. So, Consider this. Consider you've got a piece of broadcast equipment in one room in the edit suite, say, and you've got other pieces of broadcast equipment in the machine room, and they're connected together by virtue of the fact that there's a video cable that runs through the facility, through the wiring ducts, into a wall box in the edit suite, and then from the edit suite wall box there's a flying cable that connects to the back of the piece of equipment. Now remember, the earth present on the BNCs on the piece of equipment in the machine room, it carries the earth of the power supply of the machine room because it's a class 1 piece of equipment. The BNC shells are connected to the chassis of those pieces of equipment, which, because they're class 1, has to be connected to the main safety earth. And the same is true of the piece of equipment in the edit suite. Now just imagine if those earths were derived from different places. Maybe one was from a power supply that came in on the north side of the building, one was from a power supply that came in on the south side of the building, and there was a modest difference between those two earths, just a few 100 millivolts. It wouldn't be enough for you ever to notice it and get an electric shock off it. And in fact, it wouldn't impede the operation of the earth as a safety earth. It wouldn't stop fuses from blowing. It wouldn't stop residual current devices from tripping out and saving us from electrical shocks. So from a safety point of view, from what the electrician is concerned about, we're good. There's no trouble here. But when we plug, say we're taking an analog feed from a VTR in the machine room through to an analog monitor in the edit suite, all of a sudden, our 1 volt video signal, little 1 volt modest video signal, has got a couple of 100 milliamps of earth hum on top of it, and all the piece of equipment that's receiving that can do is treat it as part of the signal. It can't get rid of it, and so that's where you see big hum bars rolling up and down the monitor, and that tells you that you've got different earths in the edit suite compared to the machine room, and it's why installation engineers get very fussy about, have we got a common earth? Is the technical supply that comes into my edit suite, does the earth on that supply there go back to the same distribution board as the earth that's feeding all the cabinets in my machine room? And best practice is that it should be that way. Now, if I pop up a picture of where am I? Where's my preview window? So if I pop up a picture of we'll go back to that. Actually, I'm going to show sort of a very typical kind of wall box in an edit suite. So this is a facility that I think I was building last summer, and this is their sort of edit suite wall box. You can see there's BNCs for video in and out, and reference video, and and some audios, and some Cat 6s and some fibers down the bottom of the wall box there. Go and watch our fiber podcast. but mounted next to the wall box on the wall is a 16 amp C-form commando connector, as electricians like to call it, and that's the technical mains for that room. And so what we would do is, when the edit desk gets brought into that room, the power distribution unit within the edit desk will be fed off that 16 amp C-form, and anything that's in the production chain, monitors, the Avid maybe, the Final Cut workstation, whatever, that would all be fed off that same supply. And I know, because I specified this to the electrician, I know that 16 amp C-form connector goes back to the same breaker board as the supply that feeds the machine room. So I'm certain that the earth that's provided on that 16 amp C-form connector is the same earth that's provided to all the production equipment in the machine room. And when you're in that situation, you find yourself in the very happy position that you don't have that induced mains hum between different rooms.
Which is the bane of anybody's life. We've had all sorts of... I remember once we had a new 1-inch machine delivered from America, and the engineers wired it in. Anyway, a little bit later that day, there was a crisis, hum over everything, analog, a lot of analog equipment at that time.
Yes.
And the question was, what have we changed? Something somewhere has changed. And in that case, the wiring of our American cousins' colour scheme is slightly different to ours. And to ours, the earth and neutral were the wrong way round. So we were putting a nasty mess all over our earth.
Yes, and then that just
fixed it.
Just reminds you that the neutral and the earth are inherently tied together back at the substation, and mixing them up, you all of a sudden you've got volts on the earth now, relative to the live supply. So I'm just sort of fiddling around with the symbols for double insulated class 2 equipment I've got up on screen at the moment, and I've just popped up the symbol for class 1 just in case that wasn't clear before from the Wikipedia page. The Wikipedia article is excellent, by the way.
Okay.
So just, I suppose, a bit of a recap for what I normally specify as being the optimal configuration for edit suites, and that's having knowing that I've got the same technical earth feeding my machine room cabinets as is feeding the technical outlet in the edit suites, because if for example I had my machine room done correctly and I had just any old kind of earth from another supply in my edit suites, that's when you run into trouble. And in fact, you mentioned that 1-inch machine that you had to deal with. I was called back to a facility that we'd built, and this was a year or so after we'd finished building it, and they had hum over all their analog feeds. You couldn't look at an analog picture without seeing hum bars on it. And for 2 days, I tried to discover what was causing this. And of course, because mains is mains, you can't even take a voltmeter and go around measuring where the hum's been induced, because it's on everything, and the impedances back to earth are so tiny that there's no way of getting a relative feel about where it is being induced. So in the end, I just sort of sat down and said to myself, I've got to ask people what's changed. And eventually the receptionist said to me, a couple of days ago they moved the plasma screen in reception a couple of feet to the left to make way for something. I don't know, they were moving a door frame or something. Okay. And so when I went and had a look, the analog cable that was feeding the back of that screen had been crimped by the mounting plate as it went up against the wall. And so the screen on the video cable, which of course was carrying technical earth back from the machine room, was now tied down to the building's earth, because that plate, it's mounted on the wall. The walls, it was a stud partition wall, and so there's a steel frame within the wall. And just by virtue of the fact that the whole building sits at kind of earth potential, meant that that was the case. As soon as I went back to the machine room, unplugged that video feed, leaving the machine room, going to the big plasma screen in reception, the hum all disappeared everywhere. And I was kind of hailed the returning hero, but it had taken 2 days to find where the problem was. It's very hard to track down. And invariably, you just come back to saying, what's changed? Where are things not? Why are they not the same as they were 2 days ago?
Yeah, quite. There's a little point which I noticed from your notes. You meant that was tying the two earths together, the cooking earth and the tech earth, should be avoided.
Yes, some people try that as a way of unifying their earths, so that they're not having to put up with differences between the earths, and it works from an induced hum point of view, but it doesn't work from a noise on your mains point of view. So now every technical feed in the building is bedeviled by the cleaner, plugging a vacuum cleaner in. So that should really be avoided if at all possible. Now, one of the ways round, if you just have one miscreant feed or edit suite or whatever, where you just can't get rid of the hum, and just economics or just practicalities mean you can't put in a proper technical feed to that room, is you can get humbuckers. You can get humbucking devices, the little potted coils, which are essentially a one-to-one high frequency transformer that allows all the signal to pass through, but none of the DC offset. So all the mains hum, all that rubbish is removed. And when I've worked on OBs, OB engineers kind of keep a big bag of those things in the back of each truck, because they know that wherever they show up, it's going to be problematic.
Yeah. Well, in fact, that's how we used to have. We had two buildings either side of the road at Molinare, and lots of video going between the two of them, and everything had to be. So had a huge rack of these things, loads and loads of humbucking coils. Yeah. They did their job very well. Absolutely. And never needed the batteries changing.
And of course, nowadays, you'd say the same thing about fibre optic transceivers, because if you send video up a fibre optic cable, there's no induced earth current moving up and down that glass fibre. So go back and watch our fibre optic podcast. Yes.
That's the third mention. It was obviously a very good one.
I'll stop there.
So that's all great. How does we're looking at main safety, and we're looking at these things nowadays? We have a chap that pops around on his bicycle with his PAT testing kit.
Yes.
I think probably worth mentioning some of this.
Absolutely. So again, it became very popular in the 80s to have formalised testing of electrical installations. Very sensible it is, and it's sort of best expressed in the idea of using a PAT tester. A PAT tester stands for Portable Appliance Tester, and so it's not an appropriate device to test for fixed installations. That's the kind of thing that the electrician should do, and in fact you can't even do it unless you're Part P qualified, and unless you have that electrician's qualification, Part P qualified, you can't sensibly go and test for those things. And the electrician has a couple of devices, a gadget called a Mega, which allows him to test the fidelity, the safety of earths and things like that, and then he will write up your report sheet to show that your supply is safe. And in fact, in the same way that we mentioned, there's a demarcation between the electricity companies feed into your building in that big 100 amp fuse in a domestic premises, and those three big 200 amp fuses in a three-phase professional premises. In the same way, when you build machine rooms, you have a demarcation at each cabinet, and that typically will be the 16 amp C-form connector that powers the cabinet. Now you say, well, Phil, you've mentioned 16 amp C-form connectors an awful lot. Why are you so obsessed with these things? And I think actually they are a fantastically neat way of maintaining that segregation between technical and domestic supplies. If each one of your cabinets is fed by one or increasingly two C16 connectors, because you might have a split power supply in a big facility, you might have UPS backed power or a generator backed power, and so one supply may be the generator backed power and one supply may be just the raw mains. Then that's no piece of equipment like a Hoover or a phone charger ever comes with a 16 amp C-form connector on it. It just doesn't happen.
Somebody could come along with their caravan and plug it in.
Indeed, yes.
So if you've got squatters camping in your machine room, watch out.
That's right.
Connect to
a big cable snaked out the window to the yard outside. And in the same way, I like to maintain segregation between domestic and technical power by using IEC type connectors, C13 connectors as they're called. Although increasingly equipment's starting to have what they call C19 connectors, which is a big 20 amp style connector on the back of it. So that's how I like to maintain the segregation between the two styles of supply. But getting back to facilities with the way you do the cabinets, that's very, very typical to have that, and that would be the demarcation point where you would expect the installing engineer who's checking that this equipment cabinet is wired safely and there are no problems in it. That's the point where you'd expect him to interrupt the supply with his PAT tester and start doing his testing upstream of that 16 amp connector, through the cabinet, through all the circuits within the cabinet. And I've got a picture of a Martindale 2100, which is our preferred model of PAT tester. It's the one that we use. We have a couple of those. We use them on all our builds. And I've also popped up the test sheet that we issue. And it's a test sheet that's relevant not only for the equipment cabinet, but it can be used for an edit desk as well, and it has space to record all the circuits, and I try and construct these test sheets so that it drives the engineer through the correct way of doing it. So we've got our various tests across the top here: earth continuity, an insulation test, a run current test, a run leakage test, a flash test, and a visual inspection. And then I've got little notes above each of the columns telling the engineer what he should have connected to do that test. And then there are some score outs where you've got options. I mean, you might be testing a piece of equipment, in which case you only want to be testing its insulation at about 100 milliamps. You don't want to be testing it with lots of amps. Whereas if you're testing an equipment cabinet, it's entirely relevant to use many amps of current to do the test, because the worst thing that can happen is that you pass the earth on a piece of on an equipment cabinet. But actually, the earth was only hanging on by a single whisker of the connection somewhere in the distribution. So you want to abuse it. You want to give it a hard time while you're doing the test, and so if an engineer, if one of our guys is doing that final PAT test on an equipment bay or an edit desk, for example, if he follows my sheet here, and these grey ones have to be done for every single circuit, and these white ones are just done for the overall cabinet or for the overall desk, then kind of it leads you through it, and you do those things and get it done. So it's probably worth mentioning what the various tests are on a PAT tester.
Yes, I think that's a good idea. Yeah.
What the testing protocol is, again, this is not legally mandatory, but you would have such a hard time in court if it had been shown you hadn't done your best. If you'd commissioned a new build, a new machine room, and you just hadn't paid for this, or as the installing engineer, you hadn't gone to the extra step of doing this and certifying it to the customer. So you can see, just looking at our Pat tester here, it comes with the cord here, which is actually wrapped up inside the instruction plate. There is just a regular 13 amp mains inlet cord, and there's a 13 amp outlet, and there are various inlets. There's an IEC inlet there, and there's also an outlet for 110 volt stuff as well, because it can test both standards. And then we've got 5 buttons down the side here and a little display. In fact, let me pop up the web page for Martindale, and that may give us a bit more of it. No, it's exactly the same picture, isn't it? I suspect I pinched one from the other. But So the first button. So in fact, let's go back to our test sheet. The first button. So we've got our Pat tester behind the cabinet, and we're powering the Pat tester off the incoming supply for the cabinet, and we're powering the cabinet off the outgoing supply from the Pat tester. So the Pat tester is in effect spliced into the feed for the cabinet, and we've made sure that the mains distribution board at the top of the cabinet is turned on, and now our job is to test the 14 circuits that are being fed off that mains distribution board. And if there are 2 mains distribution boards, the other 14 or the other 12 or whatever style of mains distribution unit you like to use. So the very first thing we test for is an earth continuity test, and we'd like to see that there's less than 0.1 of an ohm of impedance between the incoming earth to the bay and the earth that reaches any piece of equipment. We'd like there to be no more than 1/10 of an ohm on the earth continuity test, That test is typically carried out at only 6 volts, but with many amps. So our machine we typically test at 8 amps, and if there's any fault within the earth path, any just kind of whiskers of conductivity hanging on, that will burn them out, and the test will fail, and you get a readout of the impedance on the machine, but it's an impedance that's been tested at a very high current, and it's something you can't do with a digital multimeter. You can't do that with your multimeter. You can't. I mean, you can make the measurement, but you can't be assured that that it's meaningful from an earth safety point of view.
Yeah.
The next thing the machine tests, and so that's a press of the button and a little readout on the machine. And in fact, more elaborate machines will record that for you. And so an electrician can take his Pat tester, or an engineer can take his Pat tester, and he can go around and do 100 things, 100 pieces of equipment, 100 equipment cabinets, or a mixture thereof, and the machine will record all this for him, and he can dump that data out at the end of the day. The 2100 we use doesn't do that; it just displays it on a meter. And in fact, earlier machines had analog swing meters that would measure it for you, but the principle's all the same. Yeah. So that's the earth continuity test, and if there's a switch on the machine, and if you're doing an earth continuity test on a particularly sensitive piece of equipment like a server or something like that, you can ramp that the current at which it does the test down to 100 milliamps, because it's perfectly allowed within things like servers and musical equipment and things like that the earth might be carried on a track on a PCB. That's allowed.
Yes, of course. Yes,
and if you're testing that at 8 amps, you run the risk of burning out, the earth within the piece of equipment. And in fact, that happened to me.
Such a thing could never happen.
Well, I don't know if you remember a band called Edie Brickell and the New Bohemians. They had their moment of fame in the late 80s, and I was working on the Late Show, which was a BBC Two. Sort of arts program, and they were performing that night, and all their equipment had been brought into the workshop for me to Pat test to make sure it was safe to use in a BBC premises, and without realising it, I Pat tested their Yamaha DX7 keyboard at 8 amps, and the thing didn't work after that. So we had to quickly send out to a hire company to get a replacement, and so my brush with fame. So the next test that the machine does is what it calls an insulation test, and we're looking for more than a mega ohm, more than 1 million ohms of insulation impedance. And what that does is it takes a 500 volt DC voltage and it applies that between the live and the neutral conductors shorted together and the earth to make sure that there's no breakdown in earth insulation. To make sure that within the piece of equipment or within the cabinet there are no points where a live conductor is so close to an earth that it could arc across. So that's the insulation test, and what we're looking for there is greater than a mega ohm, and in fact, ideally, we're looking for infinity. We're looking for an impedance that's too large to be measurable because it's going through air,
Yeah.
So that's the next thing we measure and record. The next test that the PAT tester does is a run current test, and on a single circuit within a bay, on a single IEC, C13 outlet, that should be less than 10 amps. And in fact, when we're testing bays, invariably the equipment hasn't been delivered. We are just testing the safety of the bay, and so you'll find that run current is zero, or as close to zero as the only thing that's being powered is the neon lamp in the fuse holder, of the power distribution strip. The next thing we do, very important, this is probably the most important thing from a safety point of view, is the run leakage test, and that measures the amount of leakage between the earth and the live and the earth, and the neutral and the earth, and that must be below 3.5 milliamps. And the reason for that is that if it isn't, then residual current detectors can't work. If equipment is starting to introduce leakage current, then that nice RCD that's sitting in the power distribution board, on the wall of the machine room, it's ineffective. It can't work if it's having to deal with leakage current caused by the equipment, not caused by a fault condition, but caused by the equipment. And you do see some earth leakage within a cabinet. So these results here, which I think was from a job we did just a couple of months ago. This is real life stuff. Just a bit more than a milliamp, and that's well within the spec. Now there is one big systems integrator who will remain nameless, who manufacture their own mains distribution strips. And in fact, they're manufactured in the Far East, and they're manufactured very cheaply because the live, the neutral, and the earth conductors are all running as tracks on a PCB within the mains distribution block. And with their mains distribution units, even with short length cables on the in and the out of the mains distribution unit, you get more than 4 milliamps of earth leakage. And so you've got to say to yourself, they probably don't, and they use their own brand of PDUs on all the builds they do, and you see them all over Soho and all over broadcast, and so presumably they're not actually testing these, because they'd have to hand over test sheets that said, actually, we failed on all our earth leakage measurements, all our run leakage measurements, we failed, and we can't do any better than just the PDU by itself. As soon as you start hanging cables off it, there are tiny amounts of earth leakage down cables and things like that. But their actual PDU has more than 4 milliamps, i.e. more than the allowable amount for the whole system within the PDU. And so that's why I quite like the way Bryant Broadcast manufacture their PDUs, because they're all done nicely, and you never kind of come up against this shenanigans. And they're a lot more expensive as a result.
But that's why, yes.
Now, the last test that the machine does is called the flash test, and it's an optional test. It's typically really only recommended for where you're going to be powering Class 1 equipment. And what it does is it applies 1,500 volts of AC between the phase and the neutral, the live and the neutral joined together on Earth. So in that way, it's very similar to the insulation test. But it does it using this probe, this flash probe, this thing here. And so you would typically put the flash probe onto some exposed metalwork on the cabinet, and then you press the flash button on the PAT tester, having first told all your colleagues to take their hands off the bays, because 1.5 kilovolts, although it doesn't have very much current carrying capacity, is a nasty nip.
Yes.
And so that again is another chance to test that there's no flashover to exposed metalwork and current carrying conductors. It's a further verification of the insulation, and the insulation levels haven't deteriorated. And again, it's only recommended on doing it on the big metal, on the cabinet, on the big air conditioning unit, that kind of thing. You'd never do a flash test on a piece of delicate digital equipment. And then the last test I have on the sheet that I expect the engineer to do is a visual inspection, to look at the end of the cable to make sure the connector is about to fall apart, to inspect and the earth straps that we run between the bays. And at this point, it's worth mentioning that the safest and the best build is one where you've got multiple paths back to earth. So of course you get an earth arriving at the cabinet on the incoming mains on that 16 amp C-form connector. You get the electrician, if he's done his job properly, he will also provide you with a nice chunky 2mm squared earthing strap that goes all the way back to the mains distribution board, and you should connect that to one of your bays. And you should also, the bays are bolted together, so there's great continuity between the bays. You should also run straps either at high level or at low level between the earthing lugs on the bays as well. And so now you've got multiple paths back to earth, because every piece of equipment is bolted to the bay, which is earthed. Every piece of equipment is connected to the power distribution that's coming out of the bay, which is earthed. And the bays have a different have another path back to earth via the electrician's provided strap, and you've tied all the bays together as well. So that's, you've done as best as you can. There's no more you can do in providing.
You really can't overdo it.
Yes, you've
the
kind
more
of
earths you provide, the better things are going to be. Really,
braces, another belt, and some more braces. But hey, it's for the sake of a few quid. Why wouldn't you? The BBC famously have never lost anybody. I think since 1974 to an electrical shock, and that's the kind of, although I operate in much smaller facilities, much smaller builds than that, that's the kind of record I'd kind of like to maintain. That I've never caused somebody to have an electric shock, and
No.
it is entirely achievable. If you're familiar with the legislation, and you're familiar with best practice. And you make sure you keep your records up to date, so that you know that every one of your bays has been properly pat tested, every one of your edit desk supplies has been pat tested. Quite a lot of places have an in-house policy of having all their de-riggable mains cables tested every year, and that's a good practice, although maybe a bit over the top, I don't know.
Depends what you do with them. Yes.
Yeah.
But there's also the things. Just thinking of that just reminds me of one I came across last year, in fact, which was a little IEC connector. Somebody had changed the connectors over and put the wrong gender on it, so now we had 3 prongs with live mains waiting for somebody to put their finger on.
That's a death lead, isn't it?
Yes.
That's what we call a death lead.
Just misunderstood what was asked of them, put the wrong gender on, but hadn't checked.
Yes.
Very nasty.
One of the things that I kind of keep in my rucksack the whole time is one of these little depth testers, and they're fantastic little gadgets, 15 quid or whatever, and what it does is it just measures the potential difference between live and neutral, live and earth and neutral, and that very quickly tells you if you've got a functioning earth, if you've got a and you've got volts between live and neutral, and they're the right way round. And rather splendidly, some of these more modern ones, they beep as well when things are correct. So you can literally go along a supply, bang, 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 and so long as you're hearing the beep, you know that you're well in the ballpark of things being wired correctly. Interestingly, electrical safety is one of those things where you can be fired. You can summarily be dismissed on the spot for putting a customer's life at risk. We had an engineer who it was his responsibility to do all the electrical safety testing in a build. Told me on the Friday afternoon, "Yep, Chief, I've done it all tested out fine." And on the Monday, when I was handing over to the customer, it just kind of looked like nobody had been there on the Friday. It looked like I remembered it from the Thursday night, and I thought, I'll just put my death tester on some of these supplies just to check. And I found a couple of faults, earth neutral swaps, that kind of thing, which in an extreme case could have injured a customer. And in that position, you have no other option than to let the person go, and we did. And the union ain't going to back you up on that one, kind of thing. It's the kind of thing where it's the one thing that can kill people, and you've got to be aware of it.
Yes, you must minimise the number of people you kill in a lifetime. It's just one of those things.
Ideally.
Well, it is an extremely serious, if not terribly sexy subject, but I think in that little talk that we've had there, it's actually crystallised what needs to be done. It's actually not that complicated. Even if you don't happen to own one of the PAT testing machines yourself, a word with a friendly installation guy. I can't think of any. Can you, Phil? Or even an electrician, if you can have a chat with him, will help you out.
Absolutely. Electricians, PAT testing is the kind of thing they do on downtime. They all own pat testers. They're a few £100s. They're not expensive machines. If you're a facility that can afford an engineer, you're a facility that can afford a pat tester. And you're a facility that can afford an engineer who knows how to drive it and what it's for. And if you are a facilities engineer, working in radio, television, film, data, whatever, you should really have a copy of the 17th edition on your desk and a familiarity with it that goes beyond, I watched Phil and Hugh's podcast. I can't stress enough. This is stuff that you have to get into. Yeah.
In Google's words for their recent safety thing, not safety, change in policy, this stuff matters.
Hugh, thank you very much.
It does. Are there any sort of little courses that engineers or techies in facilities can put themselves on for not a huge amount of money or not a huge amount of time, just to get themselves a refresher?
I've always done the IET's electrical safety training. I suppose really because I left the BBC in the early 90s and kind of was up to date with the BBC's level of training for the 16th edition. But when the 17th edition came out, I was kind of aware that I'd fallen behind somewhat and did the IET's 3-day course, which was fantastic. I mean, just really very good, aimed at all sort of areas of industry and hands-on and, lots of good sort of 3-day of classroom time. And I think it was £800, which, isn't ruinous,
No.
well worth doing. And in fact, the last day we had a guy from the Health and Safety Executive who had a 2-hour talk, and basically every slide he put up was preceded with, this lad, had a mains distribution board explode in his face, and it was a photograph of some poor guy in the hospital bed. He died 2 days later. This lad, managed to get himself,
great.
And it was just 2 hours of horror, and these kind of hardened electricians who are used to sort of like working on building sites. You kind of look around the room and they were just kind of blanched and white, And I think the guy did it for effect, but it was the right effect, By the end of it, we all kind of walked away thinking, "Yep, this is very serious." Yeah.
Yes. I mean, again, just from a management point of view, if you don't want to save money on the electricity bill, just take a look at how much it costs to have a legal person try and defend the indefensible, and it's considerably more than the £800 it would have cost to send your bloke on a 3-day course.
Absolutely,
it's as simple as that, really.
Did somebody say corporate manslaughter? That's the...
Yes, exactly. Well, that is a fantastic little intro and an overview of the 17th edition. And so, thank you very much. That was great.
Very good, Hugh. A pleasure as ever. I just want to say thank you to my middle boy, my 16-year-old Daniel, who's written us a little sting for the intro and the outro. So that's kind of sharpening up our podcast a tiny bit more. Any clues, Hugh, as to what our next session's going to be on?
Well, yes, there is a clue, I think, which popped in what you were saying, the death tester. It's something you keep in your rucksack, and that tickled me. A few days ago, our broadband went down, and I had a man with his muddy boots from BT, actually a very nice man from Muddy Boots Central, who came in and fixed it. It was a duff connection, not on our premises, but on a pole down the road. But in the course of hanging around and having a cup of tea and chatting, we got to talking about the stuff in his rucksack, the bits of kit that he carries. And I think a little look at what you carry in your rucksack would make a very handy little jumping off point for talking about some of the things we come across, and that will lead us into the fourth conversation, I think. So the third conversation should be, what's in your rucksack?
Fantastic. I'm looking forward to it already.